Let me ask you something. Have you ever wondered why a balloon filled with helium rises while one with carbon dioxide sinks? It all comes down to molecular mass. Hi everyone. Today we are diving into a concept that's central to chemical calculations: molecular mass. Now, what exactly is it? Molecular mass is the sum of the atomic masses of all the atoms in a single molecule measured in atomic mass units, or U. It helps us quantify how heavy a molecule is. For example, the molecular mass of water tells us how much one molecule of H2O weighs. This idea is critical when you're dealing with moles, reactions, or even gas laws because molecules don't weigh themselves, we do the math. We calculate molecular mass only for substances made up of discrete molecules like water, ammonia, or carbon dioxide. Let's look at how we do it. Alright, how do we actually calculate molecular mass? It's simple. You just multiply the atomic mass of each element by the number of atoms of that element in the molecule and then add everything up. Take water for example. The formula is H2O, 2 hydrogen atoms and 1 oxygen atom. So, that's 2 into 1 plus 16, that's 18U. Now, let's try nitric acid, HNO3. Here, we've got hydrogen, nitrogen, and 3 oxygens. So, the molecular mass becomes 1 plus 14 plus 3 into 16, which equals 63U. Each of these values comes from the periodic table. Always remember to check atomic masses before you calculate. But wait, not all compounds have molecules. Think of common salt sodium chloride. It forms a crystal lattice, not individual NaCl molecules. So instead of molecular mass, we calculate what's called the formula unit mass. What's that? It's the total atomic mass of all ions in the smallest ratio in an ionic compound. For NaCl, sodium has mass 23 and chlorine has 35.5. So formula unit mass equals 23 plus 35.5, which is 58.5 U. This gives us a representative mass of the repeating unit in the lattice structure. Let's cement this idea with a quick example: calcium chloride, written as CaCl₂. Calcium has atomic mass 40 and chlorine is 35.5. Now CaCl₂ has 2 chloride ions. So, the formula unit mass is 40 plus 2 into 35.5 equals 40 plus 71, that's 111 U. This is the weight of the smallest repeating unit in the calcium chloride lattice, even though it doesn't exist as a separate molecule. Formula unit masses help in stoichiometry, empirical formula derivation, and more. You might be thinking, why do we even care about these numbers? Well, in real life, molecular mass plays a huge role. In the lab, it helps convert mass to moles, the universal currency of chemistry. In industries, say fertilizers, if you want to produce 1 ton of ammonia, you need to know exactly how many moles that corresponds to. In medicine, drug dosages are based on molecular mass to ensure precision. And in rockets, hydrogen is preferred because its molecular mass is just to extremely light, allowing greater lift. So yes, a tiny number on paper can power space travel. Let's quickly revise what we've learned today. Molecular mass is used for compounds with distinct molecules like H2O or CO2. Formula unit mass is used for ionic compounds like NaCl or CaCl₂, which exist as lattices, not molecules. In both cases, we sum up the atomic masses of the atoms or ions present, and the result is expressed in atomic mass units, U. The key is knowing which kind of compound you're dealing with, molecular or ionic, before you pick the right method. I hope this session helped you appreciate how molecular and formula unit masses are the quiet mathematicians behind every chemical reaction, whether in labs, industries, or even inside your body. Catch you in the next class where we'll dive into even more exciting chemical connections.